Rossby waves, also known as planetary waves, are a natural phenomenon in the atmosphere and oceans of planets that largely owe their properties to rotation. Rossby waves are a subset of inertial waves. Atmospheric Rossby waves on Earth are giant meanders in high-altitude winds with major influence on weather. These Rossby waves are associated with pressure systems and the jet stream. Oceanic Rossby waves move along the thermocline, that is, the boundary between the warm upper layer of the ocean and the cold deeper part of the ocean. Rossby wave types. Atmospheric waves equals. Atmospheric Rossby waves emerge due to shear in rotating fluids, so that the Coriolis force changes along the sheared coordinate. In planetary atmospheres, they are due to the variation in the Coriolis effect with latitude. The waves were first identified in the Earth's atmosphere in 1939 by Carl Gustav Arvid Rossby, who went on to explain their motion. One can identify a terrestrial Rossby wave in that its phase velocity always has a westward component. However, the wave's group velocity can be in any direction. In general, shorter waves have an eastward group velocity and long waves a westward group velocity. The terms barotropic and baroclinic Rossby waves are used to distinguish their vertical structure. Barotropic Rossby waves do not vary in the vertical, and have the fastest propagation speeds. The baroclinic wave modes are slower, with speeds of only a few centimeters per second or less. Most work on Rossby waves has been done on those in Earth's atmosphere. Rossby waves in the Earth's atmosphere are easy to observe as large-scale meanders of the jet stream. When these deviations become very pronounced, they detach the masses of cold, or warm, air that become cyclones and anticyclones and are responsible for day-to-day weather patterns at mid-latitudes. Rossby waves may be partly responsible for the fact that eastern continental edges, such as the northeast United States and eastern Canada, are colder than western Europe at the same latitudes. Fluid-propagating atmospheric waves. Deep convection and heat transfer to the troposphere is enhanced over anomalously warm sea surface temperatures in the tropics, such as during, but by no means limited to, El Niño ±0 events. This tropical forcing generates atmospheric Rossby waves that propagates fluid and eastward and are subsequently refracted back from the pole to the tropics. Fluid-propagating Rossby waves explain many of the observed statistical teleconnections between low-latitude and high-latitude climate, as shown in the now classic study by Hoskins and Caroli. One such phenomenon is sudden stratospheric warming. Fluid-propagating Rossby waves are an important and unambiguous part of the variability in the Northern Hemisphere, as expressed in the Pacific North America pattern. Similar mechanisms apply in the Southern Hemisphere and partly explain the strong variability in the Amundsen Sea region of Antarctica. In 2011, a Nature Geoscience study using general circulation models linked Pacific Rossby waves generated by increasing central tropical Pacific temperatures to warming of the Amundsen Sea region, leading to winter and spring continental warming of Ellsworth Land and Marie Byrd Land in West Antarctica via an increase in advection. Oceanic waves Oceanic Rossby waves are large-scale waves within an ocean basin. They have a low amplitude, on the order of centimeters to meters, compared to a very long wavelength, on the order of hundreds of kilometers. They may take months to cross an ocean basin. They gain momentum from wind stress at the ocean's surface layer and are thought to communicate climatic changes due to variability in forcing, due to both the wind and buoyancy. Both barotropic and baroclinic waves cause variations of the sea surface height, although the length of the waves made them difficult to detect until the advent of satellite altimetry. Observations by the NASA CNESTOPEX Poseidon satellite confirmed the existence of oceanic Rossby waves. Baroclinic waves also generate significant displacements of the oceanic thermocline, often of tens of meters. Satellite observations have revealed the stately progression of Rossby waves across all the ocean basins, particularly at low and mid-latitudes. These waves can take months or even years to cross a basin like the Pacific. Rossby waves have been suggested as an important mechanism to account for the heating of the ocean on Europa, a moon of Jupiter. Waves in astrophysical disks Rossby wave instabilities are also thought to be found in astrophysical disks, for example, around newly forming stars. Definitions. Free barotropic Rossby waves under a zonal flow with linearized vorticity equation equals, to start with, a zonal mean flow, U, can be considered to be perturbed where U is constant in time and space. Let be the total horizontal wind field, where U and V are the components of the wind in the x and y directions, respectively. The total wind field can be written as a mean flow, U, with a small superimposed perturbation, U, and V. The perturbation is assumed to be much smaller than the mean zonal flow. Relative vorticity, U and V can be written in terms of the stream function. Considering a parcel of air that has no relative vorticity before perturbation but with planetary vorticity F as a function of the latitude, perturbation will lead to a slight change of latitude, so the perturbed relative vorticity must change in order to conserve potential vorticity. Also the above approximation UU ensures that the perturbation flow does not advect relative vorticity. With plug in the definition of stream function to obtain. Using the method of undetermined coefficients one can consider a traveling wave solution with zonal and meridional wave numbers k and l, respectively, and frequency. This yields the dispersion relation. The zonal phase speed and group velocity of the Rossby wave are then given by where c is the phase speed, is the group speed, u is the mean westerly flow, is the Rossby parameter, k is the zonal wave number, and l is the meridional wave number. It is noted that the zonal phase speed of Rossby waves is always westward relative to mean flow u, but the zonal group speed of Rossby waves can be eastward or westward depending on wave number. Meaning of beta equals, the Rossby parameter is defined. Is the latitude, I per mil is the angular speed of the Earth's rotation, and a is the mean radius of the Earth. If there will be no Rossby waves. Rossby waves owe their origin to the gradient of the tangential speed of the planetary rotation. A cylinder planet has no Rossby waves. It also means that at the equator of any rotating, sphere-like planet, including Earth, one will still have Rossby waves, despite the fact that, because quasi-resonant amplification of Rossby waves. It has been proposed that a number of regional weather extremes in the northern hemisphere associated with blocked atmospheric circulation patterns may have been caused by quasi-resonant amplification of Rossby waves. Examples include the 2013 European floods, the 2012 China floods, the 2010 Russian heat wave, the 2010 Pakistan floods and the 2003 European heat wave. Even taking global warming into account, the 2003 heatwave would have been highly unlikely without such a mechanism. Normally freely traveling synoptic scale Rossby waves and quasi-stationary planetary scale Rossby waves exist in the mid-latitudes with only weak interactions. The hypothesis, proposed by Vladimir Ptaukov, Stefan Rahmstorff, Stefan Petri, and Hans-Joachim Schönhuber, is that under some circumstances these waves interact to produce the static pattern. For this to happen, they suggest, the zonal wave number of both types of wave should be in the range 6 to 8, the synoptic waves should be arrested within the troposphere and mid-latitude waveguides should trap the quasi-stationary components of the synoptic waves. In this case the planetary scale waves may respond unusually strongly to orography and thermal sources and sinks because of quasi-resonance. It is also suggested that the phenomenon is made more likely by anthropogenic global warming, but the EEA has cautioned that more data would be needed to confirm that specific events such as flooding were caused by global warming. See also, atmospheric wave, equatorial waves, equatorial Rossby wave, mathematical treatment, harmonic waves, Kelvin wave, polar vortex. References. Bibliography, Rossby, C.G. Relation between variations in the intensity of the zonal circulation of the atmosphere and the displacements of the semi-permanent centers of action. Journal of Marine Research 2, 38 doi, 10.1357/0022240398066499023. Platzman, G. W. The Rossby Wave. Quarterly Journal of the Royal Meteorological Society 94, 225. Bibcode, 1968 QJRMS 94225P doi, 10.1002/QJ 49,709,440,102. Dickinson, R.E. Rossby waves, long-period oscillations of oceans and atmospheres. Annual Review of Fluid Mechanics 10, 159. Bibcode, 1978 and RFM 10159 DDoI, 10.1146/ANNUREVFL. 10.010178.001111. External links, description of Rossby waves from the American Meteorological Society, an introduction to oceanic Rossby waves and their study with satellite data.